All right, this is a video on our notes for writing equations of polynomial functions. So this is divided into sections. We have first degree polynomials, first degree polynomials, which is a linear equation, second degree polynomials, which is a quadratic equation, so on and so forth. So they're divided and then from graphs. Okay, so the directions here are write an equation of a polynomial function for each set of conditions. If the situation is impossible, state this. In many cases, there's an infinite number of possibilities. So like the answer that we're writing down might not be the only answer. It might have more answers to that. And we're just coming up with one, okay? So these are all linear equations. So we want to make sure that the degree is 1 when we're done writing it. So the first one is writing a linear equation that crosses the x-axis at x equals 3. So we want to have a x-intercept of 3, so that would be x minus 3. And you don't need the parentheses, so that give us a 0 of 3. That gives us a factor of x minus 3. So you don't need the parentheses there, right? Like you can be like, oh yeah, I don't even need those when I'm done, if you want, okay? But that is one solution, or that's one answer there. All right, bounces off the x-axis at x equals -2. Now remember, these are linear equations. It's a straight line. You can't bounce off the x-axis. So this one is not possible. And once again, is because you can't bounce and it's a line. C, does not touch the x-axis. So if I want an equation of a line that doesn't touch the x-axis, it has to be parallel with the x-axis. So it's going to be a horizontal line. A horizontal line are all y equals. So y equals any number other than 0, because if it's 0, it touches the x-axis on unlimited or infinite amount of time. So I'll do y equals 3. Okay. All right, next we're on to quadratic equations, which are what we're more used to with this bouncing and touching. These are the ones that have curves, right? So this is passes through the x-axis at x equals -2 and x equals 6. I'm going to start off with y equals. If -2 is a 0, then x plus 2 is a factor. If 6 is a 0, then x minus 6 is a factor. And it doesn't say it has to be in standard form. So you can have your answer like this, or you can write it in standard form, y equals x squared minus 4x minus 12. It's up to you. It doesn't say what form it has to be in. All right, next, bounces off the x-axis at the 0 of -4. So we have y equals, if -4 is a 0, then x plus 4 is a factor, and if it's bouncing off of it, that factor repeats twice. If I want it to be a quadratic, right? All right, does not touch the x-axis. So if you think about it not touching the x-axis, we want no real zeros. So we can't have linear factors. So what we're going to have to do is we have to make a quadratic factor, so x squared, and it would have to give us imaginary solutions. So x squared plus, and then any number here, 1, 2, 85, it doesn't matter. I'll do 3 again. And then once again, you don't need those parentheses because it's just that one factor. Okay. All right, moving on to the next section, we want cubic equations. So these should all have a degree of 3 when we're done. Crosses the x-axis. So we're going to all have multiplicity of 1 here. If there's a 0 at -1, then there's a factor at x plus 4. Or sorry, x plus 1, x plus 4, and x minus 3. And if you look here, this is a cubic function because the exponents are 1, 1, and 1, and x to the first times x to the first times x to the first is x cubed. Bounces off the x-axis, so y equals, bouncing off the x-axis is going to have a exponent of 2, 4, 6, 8, something like that, but since we want it to be a cubic function, we know it has to be a 2. X minus 2 would be the factor, and then it also passes through at x equals 3, so x plus 3 is a factor. Passes through x equals 4, so that's x minus 4 is a factor, with no other zeros, would mean that, so I have to get my y equals here, would mean that I want this to give me imaginary zeros. So I'm just going to use that x squared plus 3 again, right? That's going to give me imaginary zeros. That's going to give me a 0. I'm pointing to it. That's going to give me a 0 of x equals 4. And if you look, if you multiply this out, this is first power, this is a square. That's going to give me my x to the third power. All right, next one does not touch the x-axis. So that would mean that I need imaginary zeros, like x squared plus 3 again. That'll give me 2 imaginary zeros. But then to not touch the x-axis again, I would need another imaginary 0, and imaginary zeros always come in complex conjugate pairs. So there's no way to not touch the x-axis with a cubic function. So this is not possible. If it was quartic, I could do it, but not for cubic. Speaking of quartic, here's some quartic. So we have y equals crosses the x-axis at those 4 places. So we have x equals -2, so x plus 2 is a factor. X equals 0, so x minus 0, or just x, which I'll write in front because it looks better, is a factor. X minus 3 is a factor, and x minus 7 is a factor. All right. Next, bounces off the x-axis at -2 and 3. So y equals, bounces off the x-axis at -2, so that's x plus 2 twice, and x minus 3 twice. And this is quartic here, and if I look at the one above, it's also quartic. Y equals, bounces off the x-axis at +1, so x minus 1 is a factor, and then goes through -3 and 4, so x plus 3 and x minus 4. Next one passes through at x minus 1, or x equals 1. Oh my gosh, x equals -1, so x plus 1 is a factor. And then -5, so x minus 5 is a factor. And then no other zeros. So notice right now I just have a quadratic. If I want it to be a quartic, I have to get 2 more zeros. They're going to have to be imaginary if I don't want any real zeros. So I'll use my x squared plus 3 again. Okay, does not touch the x-axis. So the other one we did was cubic, and we talked about this already. This is quartic, so I'm going to have imaginary zeros, right? There's 2 imaginary zeros, and then I need another 2 imaginary zeros. So I'll do x plus 5. Okay, so that's 4 imaginary zeros, not touching the x-axis. All right, so here's an assorted, like just a bunch of different kinds here. So y equals a bounce at x equals 2, so x minus 2 is a factor. And if it's bouncing, I have to have an even exponent, so I'm just going to use 2, why not? Cube root at 0, so that's x to the third power. I'm going to write that in the front because, there we go. A cubic root at 0. And passes through -1, so a factor of x plus 1. That'll work. And if the directions were of least degree, then those are the x ones I definitely want to use. If it doesn't say of least degree, this could be any even number and this can be any odd number. Has a bounce point at -3, 1, and 4. So x plus 3 squared, x minus 1 squared, x minus 4 squared. Once again, it doesn't say of least degree, but if it did, those are the x ones I definitely want to use. And then it says, and y is less than or equal to 0 for all x. So I want it to give me a negative output every single time. So right now, if you think about what this looks like, a sketch of this, we have zeros at -3, 1, and 4, and it touches, right? And it is an even degree, so it's upward facing, and then it bounces. And this is all positive, and I want it to be down here, bounces. So I need to reflect it or make a negative leading coefficient. So I'm just going to scooch this over and put a negative in front. It could be any negative number in front. All right, a cubic function with a linear root at x equals 2. So y equals, that's going to be an x minus 2, linear root, so just exponent of 1. And then no other points of intersection with the x-axis. So real, no thank you. We want imaginary. So x squared plus 3. And you can use any number there, right? As long as it's plus something, because minus something will give me real solutions. All right, fourth degree, so quartic, passes through linearly at x equals -1, so x plus 1 is a factor. Linearly means exponent of 1. X minus 4 is a factor. And then no other points of intersection, so imaginary zeros. So I'll change it up and put 8. Polynomial of lowest degree that has x-intercept at -3, so that means there's a factor at x minus 3 with multiplicity of 2. Y equals 0 at 5, so x minus 5 is a factor with multiplicity of 3. And 0 at x minus 4, so x plus 4 is a factor with a multiplicity of 1. Voila. All right, last one, and then we'll do this from a graph. Find a polynomial with a degree of 5, having a cubic factor, so y equals cubic factor at x equals 0, so that's, so that's a factor of x plus 2, cubic factor. A 0 with a multiplicity of 2 at x equals 3, so a factor of x minus 3, multiplicity of 2, so there's my 5th degree polynomial, and a y-intercept of 48. So 0, 48. When I plug in 0 into my function, I have to get 48. So let's check to see if I'm getting that. I plug in 0 for x, right? So I plug in 0 for x, and I have to get 48. So if I plug in 0 here and here, right? So 0 plus 2 is 2. 2 cubed is, I don't need those. Well, let's try that again. I meant to erase, not cross that off. All right, so I plug in 0 here. 0 plus 2 is 2. 2 cubed is 8. Plug in 0 here. 0 minus 3 is -3. -3 squared is 9. So the question is 8 times 9, 48? No. So I need to come up with a number here, which we'll call A. So 0 times 9 times 8 has to be equal to 48. So that I need to come up with this number so I can write it right here. So I'll just solve this equation. 48 equals 9 times 8 is 72. So 72 times A. Divide by 72. And I get A is equal to 48 over 72, which is simplifiable. 24 goes into both. 24 goes into here twice. 24 goes into here 3 times. So 2/3. There you go. I don't know why I'm boxing this one and no other ones. Okay, so lastly, we have to do it from a graph, which is very similar to what we just did. So first off, it's asking us to determine the end behavior. So we're going to say as x approaches -infinity, this is f of x, so we're going to say f of x approaches. And if you look, this is facing upwards, so positive infinity. I'm going to copy this and paste this. So as x approaches positive infinity, f of x approaches. So if you look at this, the other end is also pointing upwards, so I'm going to keep that as positive infinity. I'm going to do the other one here, or I'm going to copy and paste this at least, copy, paste, and then I'll erase these for the future. And that's called g of x, so I'll erase those for the future. G of x, g of x. Okay. All right, determine the least possible degree. So what you're going to use from the graph to determine the least possible degree is the number of turning points. So when it goes from positive infinity to negative infinity, when it goes from increasing to decreasing, or decreasing to increasing. So right here, that's a turning point, turning point, turning point. So there's 3 turning points. That means the least possible degree is one more than that, which is 4. So we are going to write a 4th degree polynomial. Okay, locate the zeros in their multiplicity. So we have x equals, that's supposed to be -5, be kind. Since it crosses, it's odd. X equals, be kind, that's -1. Crosses, so it's odd. Be kind, that's x equals 3. It crosses, and x equals 5. I know that those are terrible. I'll fix them for next period, or for when you get them in class. X equals 3, x equals 5. God, those are really bad. And we're going to say that they cross, so odd, odd. I know it's not beautiful, okay? I'm aware. All right, so we have to create a function to fit this graph. Now, we can get the factors pretty easily. Y equals, these are our zeros, so x plus 5 is a factor, x plus 1 is a factor, x minus 3 is a factor, x minus 5 is a factor. They all have an odd multiplicity, so I'm going to leave them as 1, 1, 1, 1, 1, okay? But I also can see that, oh my God, the y-intercept is supposed to be 0, 2. This is the worst graph I've ever seen. I think it's supposed to be, no, it's supposed to be 0, 1. I'll fix it before you ever see it. But it's 0, 1, shh, okay? It must have just got knocked a little bit, but it's supposed to be 0, 1. So the y-intercept is 0, 1. That means when I plug in 0, and if I change it because I fix it, because this is a horrible graph, you'll still get the idea, okay? When I plug in 0 into this equation, I have to get 1, okay? So let's plug in 0 and see if we get 1. So we have 4 places we have to plug in 0. Here, oops. 1, 2, 3, 4. And I have to see if it's equal to 1. So if I plug in 0 here, I got 5. If I plug in 0 here, I get 1. If I plug in 0 here, I get negative 3. If I plug in 0 here, I get negative 5. That is 5 times 5 is 25 times 3 is 75. Positive, positive is still 75. So I get 75 is equal to 1, which is not true. So we have to come up for a number right here that we can multiply 75 by to get 1. So to solve for that, divide both sides by 75, and we have 1/75. And if it's at 2, then it's 2/75, but I don't know what it's supposed to be at, to be honest with you. I'm gonna fix it, but that's what it is. Is this one better? No, it's not. It's better. All right, last one here. So the limit as x approaches negative infinity is negative infinity because this is facing downward. Positive infinity because this is facing upward. The least possible degree, count the number of turning points. So that's 1, 2, 3, 4. So the turning points is 4. So add 1 to get the least possible degree, which is 5. The zeros in their multiplicity, so there's one here at negative 4, here at 0. X equals negative 4, x equals 0, x equals 5 and 6. Ugh. Sorry, I know it's bad. All right, crosses at negative 4, so odd. Crosses at 0, so odd. Bounces at 5, so even. Crosses at 6, so odd. All right, so we're gonna do, I put y equals, this was f of x. Let me go back and fix this. F of x equals. And this one is g of x equals. G of x equals. Leave a space in case you have to squeeze that leading coefficient. All right, so x plus 4 is a factor, which is odd, so I'll leave it as a 1. X is a factor, because x minus 0, right? It's odd, so leave it as a 1. 5 is a 0, so x minus 5 is a factor, even, so I'm going to square it. And then 6 is a 0, so x minus 6 is a factor, odd, so I'm going to leave it as a 1. Oh, also, I said the least possible degree is 5, and if you look, this degree is 5. Okay? Now I just have to make sure that the end behavior and the coefficient matches. So if you look at what this is, it's 0, 0, the y-intercept. So when I plug in 0 for x, I have to get 0 for y. So let's check to see if we do. We have 1, 2, 3, 4 places, and we have to get 0. So we have 0 times 4 times 25 times negative 6, which is 0. Check. So I do not need to put like a 1/75 here. We don't have to solve for it. Like if this was a 2, then I would have to multiply this out, divide, get a here, divide both sides, but it's 0 equals 0, which is true. One thing I do have to check though is the end behavior to make sure it's a positive lead coefficient. And if you look, if I were to connect these two, it's like a positive slope line. So it is going to be positive, and that's our final answer. Okay. All right, so that's it for today. I will fix that graph for our notes. So if yours looks better, it's because I couldn't live with what it looked like. All right, get started on the homework.